press record. Yay, we're doing it. Okay, well, hi everyone. On behalf of Christian and Pavel and myself, thank you for coming to our first graduate student colloquium of the semester. Thank you very much to Brendon Madison, who has agreed to give our talk today. He's just starting his third year as a graduate student at KU, where he recently defended his master's, which is very exciting. So congratulations, first off. And I guess with that, I will just let you take it away to talk about CubeSat-1's quest for cosmic rays.
Okay, thank you, Mindy. Yeah, so CubeSat-1's quest for cosmic rays. Hopefully this will be fun. So just some contents. I'm gonna do the world's fastest self-promotion, and then go over some context of the CubeSat-1 mission, talk about the PCRD for probably most of the time, and then the Monte Carlo simulation I built for it, as well as I'll just sneak in this bit at the end about potential future mission stuff, and then add in a conclusion that really is very basic, and then the references, acknowledgements, although there aren't links. Yeah. So this is our roadmap. So my self-promotion is essentially I don't have an advisor anymore. Also, I learned that space law was a thing and that you can't just do whatever you want in space. Yes, indeed. Proud self-promotion. So essentially, right now my research is just PCRD because that's my own research, and more or less I'm looking for an advisor. That's where I'm at. And I have all this experience. I just don't know where to go with it, but I have 6 months to figure this out. So I don't know. If anyone has an idea of maybe what I should do, yeah, I'm all ears. But yeah, I PCRD, and obviously that's not full time, although maybe it should be full time. I don't know. But let's get into the context. So CubeSat-1. So I'm putting launching soon because at this point I've been told that I shouldn't give out all the specifics of CubeSat-1 because there are certain things that we can get in trouble for sharing. And also, to my surprise, as well as the surprise of basically everyone in the CubeSat collaboration, we actually had an attempt of someone trying to perform what was essentially espionage, although very poor espionage. So there are certain things that should not be talked about in great detail, like when and how we are launching. But we can talk about the fact that the previous launch, I need to click on this, previous launch failed. It blew up somewhere over, I think, Russia. So that was unfortunate. And that was back in 2005. But now we are trying this again, essentially. And we're going to get a hopefully somewhere close to 550 kilometer sun synchronous polar orbit. So to explain what that kind of orbit is like, because you have tons of different orbits, this line here is what an equatorial orbit looks like. So you have Africa over here, and so the equator goes, through here. This is South America, North America. So this is just your standard equatorial orbit. This is what a polar orbit looks like. And as you can imagine, a polar orbit will also precess in a certain way. If that precession matches the precession of the sun, then it is solar synchronous. So this is more or less what our orbit is. It precesses with the sun at 550 kilometers. To put things into more perspective, though, we can talk about the particular CubeSat. We have a 3U CubeSat. Here's an image of what that looks like. This is from Tyvak Nanosatellites, who are the people who provided us with a CubeSat. Although they really technically only gave us the frame. So all these like solar panels and everything, we have different solar panels. Um, but essentially you get like 30 by 10 by 10 cubic centimeters of volume and around 3 kilograms of mass and less than 5 watts of power. So you don't have a lot to work with. And also because we're mostly student organized group, we don't have like a lot of money or support. So our payloads are also like pretty cheap. And we're really just kind of focusing on, can we demonstrate like some redeemable physics and engineering? So what exactly is up at that 550 to 450 or so orbit area? Because that is what low Earth orbit is for at least this discussion. Well, we have a bunch of particles and we also have some plasma sources. So to break it down, we have cosmic rays, which are essentially high energy. They're coming in from all sorts of directions. They're flying through the Earth's magnetic sphere or magnetosphere, and some of them even fly through like Earth's atmosphere. Um, these are the particles that the PCRD is trying to measure. But in addition to that, we have these lower energy solar energetic particles um, and these sort of trapped Van Allen belt particles that we don't really want to measure in PCRD, but they're definitely there. And because they are there and they're lower energy, we actually have a bit of shielding to sort of stop these from saturating the PCRD detector. Um, but we also have plasma sources. So these are typically over the polar regions, um, as well as just the ionosphere itself is a kind of plasma in ways that can interact with spacecraft as well. Like you can have spacecraft charging, and if a spacecraft charges too much and then discharges, you can get destruction within or on the surface of your spacecraft, which obviously is bad. There are also these interesting high velocity plasmas that I learned about recently that were called Steves. So you essentially have two particle species, an electron and a ion um, plasma that go along each other, and they travel at like kilometers per second in the Earth's like uppermost part of its atmosphere. So if something like this hits, it looks pretty, but if this hits your satellite, it could potentially do a lot of damage because it's a high velocity plasma. It's it's still like fairly low density, but um, in space orbit, most things are low density. Um, so it's still pretty dangerous. Um, but to like really get in like the particles, where are they coming from, where are their energy at their energies. I have this like flux in logarithm versus energy in logarithm, and at really low energies, the electrons kind of have this dominance, but the protons and the nuclei become more dominant at higher energies. What's kind of interesting about this plot is that even though you have all these different, like galactic cosmic rays, solar energetic particles, Van Allen belt particles, all these different sources, there's still kind of a general like negative log trend, which is kind of cool. At least I think it's cool. And it really kind of helps you understand that, okay, well, at really high energies, like this is a GeV. So PCRD is going to be looking at like around here and to the right. You still have a lot of particles here. Like this is per square meter per second, 10 to the 5. Like that's still a lot of particles. So even on a CubeSat, which isn't that large, you really still get a lot of events. But this is even more complicated because you have to break this down in terms of lat long. Um, in particular, the solar energetic particles tend to come in around the polar regions unless you have some like serious solar activity going on, because these are the regions where the magnetic field switches direction to essentially be going up and down. And so you actually can have that flux of particles come in. And the in addition to this, you also have the Van Allen belt particles, which normally you think of the Van Allen belts as being much further out in space than low Earth orbit, but there are Van Allen belt particles that manage to get down into low Earth orbit, particularly for electrons around the poles and in this anomalous region that you also see with the protons, which this is called the South Atlantic anomaly. It's just a anomalously low magnetic field density area that it just kind of sits in this same lat long spot. It's kind of an interesting anomaly, but it allows those Van Allen belt, inner Van Allen belts to really go further down into Earth's atmosphere than what they usually would. So again, what are our objectives? Well, broadly, we want to measure primary cosmic rays, and we've kind of been working towards that since 2016, whenever it was a chapter research proposal. So take a step back and zoom into this diagram on the top right to kind of fully understand what is a primary cosmic ray, because here at Earth's surface, we talk about cosmic rays and we typically mean these two particles, neutrinos and muons. Like, unless you're going to really, really high energies, and then you can get like other types of particles that will fly through the entire atmosphere. But in general, the cosmic rays at the Earth's surface that you talk about are typically muons or neutrinos. And because neutrinos are weakly interacting, usually you're just talking about the muons, because those are the ones that will actually interact with things, so you can actually measure them in your detector. So like if you're setting up like if you're sitting at the LHC and you're looking at like background radiation as you're like waiting for the beam to turn on so you can take actual data, you're probably looking at like muons. But those are coming off of the primary cosmic rays that for the most part are protons that are hitting the upper atmosphere and creating this shower of secondary particles. Okay, so PCRD is going to be like up here in space. And we're going to be hoping to measure some of these like protons and nuclear particles. Okay, these heavier particles. We want to try and to be some first like a HEP payload from an American university, and also use pulse shape discrimination that I'll get into later to really try to differentiate these particles, these cosmic rays, and their energies. Then in general, this also just kind of has a lot of applications to other things. It's compact, which to verify that this is the housing, this it may not be that clear because the tape measure is like further back from the housing, but this dimension here, and then I right click to immediately erase it because I'm a pro. This is 7 centimeters, okay? So it's a small detector. It fits in the palm of your hand, unless you have the world's smallest hands. So it's small, but if a high energy particle flies through it, you get a pretty good idea of what that particle is. So that has a lot of advantages for a space platform where you're going up into space and the high energy particles that you can't shield yourself from are going to fly through you. You'd like to know where they're coming from and what particles they are, because then if you're going to build additional shielding, because maybe you're colonizing the moon, for example, having something like this that can tell you, oh, it's mostly electrons from this direction or that direction, really helps you in trying to build that additional shielding. So this is something that is potentially useful for future space missions, because as I am trying to demonstrate with this top right plot that I'll get into how I made this in in a little bit. This is like a right ascension. So this is RA, and I'm going to try to. I'm like, even when I use a stylus, I still cannot write at all on a computer. This is declination. So this is essentially like a celestial sphere plot, to put it another way. And even whenever I put like the sun here and the moon here, and these are just like random particle events, you can get some idea of, okay, well, the sun's probably in this direction, even though like the astronomers probably know, the sun is like the width of your pinky at arm's length or whatever, it's like 50 arc minutes or whatever. It's very small. And so it's only like a pixel or something, or a few pixels on this plot. But even still, we have a general idea that, okay, it's probably down here where there's this overabundance of events. And so even a very poor angular reconstruction is still an angular reconstruction that could have some utility in a space mission. But in order to do that, we need these fancy scintillators, which is why I've put this CAD here. And how this works is particle flies through this scintillator and it generates a bunch of light. This light sort of scatters around, but importantly, it'll hit this paraboloid surface, which has a focal point that's like right below the CPM, this photomultiplier. So the light will bounce around a bunch and eventually find its way to the photomultiplier, so you can get all that light. But I'll get into that in more detail later. Why might we want to do this, build such a thing? Well, you can really sort of see why if you look at NASA fiscal year 2020 reports. Like this one on the left, I just love this so much. So NASA creates this objective that is about more or less monitoring space radiation and health risks for exploration. Their performance indicators, this top one is about exercise in space. This bottom one is about developing like food systems in space. So their solution doesn't involve addressing the big problem at hand of, hey, how do you survive even though there's lots of radiation? Instead, they're doing the very American thing of, let's ignore that this is a problem and instead focus on exercise and food. Like, we don't need to worry about the radiation that'll kill us. We just need to exercise more and eat more food. Just, I don't know. Like, I hope this is a typo, but it was in their report. So it just seems kind of silly. But in addition to this, there's also 12 objectives in the Artemis 3 report that lay out measuring background radiation, i.e. cosmic rays in some capacity. These two in particular are like the hard physics ones, where probing the universe at the highest energies and literally measuring cosmic rays. These are like pure physics. The other 10 are like doing something else, but also measuring cosmic rays, because they want to know, like, okay, does the moon change, the surface of the moon change in response to cosmic radiation? That sort of thing is one of them, from what I remember. So there are 10 of those in these two. So clearly it's important to NASA. And I mean, really, it should be important to anyone who wants to do something in space, considering, or for example, on the moon, where 9 days on the moon is nearly 4 times the radiation of 1 year on Earth. Okay, so what this comes down to is, depending on how bad the radiation environment is on the moon, like where you are on the moon, what the geomagnetic and solar activity are, you could have 100 to potentially 100 days to like 2 years before you die of radiation poisoning or complications of radiation. So clearly, better understanding it is kind of important if you want people to live on the moon for a long time. So what kind of particles above 1 MeV really in low Earth orbit? And that's just more or less it. Now, for the most part, there have been previous measurements of this sort of thing, but there's not a great idea of like what angles all these particles are coming in at. Like I looked through AMS and Pamela's, a lot of their papers, and I couldn't find anything that was like, okay, in this direction there are these particles with this flux, in this direction there's this particle with this flux. I couldn't find any angular spectra. Okay, and it really kind of makes sense because if you look at these detectors, they were meant to be more or less fixed in place and have this vertical orientation. Okay, particle flies in from the top to the bottom, and so you're really just looking in one direction, either up or down. Although for the most part, just up. But I mean, technically, there's nothing stopping a particle from flying up through the ground through this detector, because if it's high enough energy, it definitely can do that. Um, but I mean, in addition to this, there's also like, this is really out there, but maybe we measure the AMS. They saw way too many positrons, and then they claim that this is dark matter. It's kind of out there to me. But if we got enough data, because we're able to run long enough, we could help further constrain this positron excess, see if it really is a positron excess and not like something else. But why might you want to look out in different directions and do this sort of thing? Well, for one thing, even if you believe like this is, these particles are isotropic, that doesn't really make a whole lot of sense because there's still a geomagnetic field. So there should be some curvature in the trajectory of these particles, right? If they're charged and they interact with the magnetic field, they get curved. So it doesn't really make sense that any direction should be the same. At least it doesn't make sense to me. Maybe there's a better argument there. So just being able to look out in all these directions and see like what particles are in what directions is kind of a demonstration of physics, which is really, again, what we're trying to do here. So what are scintillators? Why are we using them? So they're pretty cheap and they're highly customizable. They emit light when high energy particles fly through them, okay? And how much light they emit, as well as how fast they emit that light, is based off of the chemical composition of the scintillator. In general, scintillators tend to have these benzene rings. And for anyone who doesn't know chemistry, that sentence means nothing to you. Essentially, there's like these hexagonal carbon rings. And for one reason or another, those are really good at taking radiation and turning it into light. So you put a whole bunch of these together in a plastic material, usually, and you can generate a lot of light from radiation. Okay. So again, I can draw that sort of diagram as I did before. Particle goes through, you get a bunch of light. It all eventually focuses on the CPM. Now, why do we want to focus all of it on the CPM? Because normally with scintillators, you just want a sample of that light to know that the particle flew through your detector. You don't really want to use a scintillator for calorimetry, because in order to do that, you have to get most of the light, or at least a really good sample of the light. And that's really what we're doing here. Okay, so that's why we're not just using this to like tag particles. We're also trying to measure their energy. So we need to get most of that light. But in addition to scintillation, which is that process of particle flies through, you get light, there's also Cherenkov radiation, because this scintillator has an index of refraction, and these particles are relativistic. In many cases, they are flying faster than the speed of light in that medium. So that medium wants to slow them down. The what's the word I'm looking for? The manifestation of that slowing down process is Cherenkov radiation. Okay, so we really have two forms of radiation going on here, both scintillation and Cherenkov. And because of that, we can use this radiation gain parameter that I've come up with, and is what I'm using to get the shape of these pulses. And I use this fancy like mathcal R. But essentially, it's in decibels, a ratio of the scintillation to Cherenkov radiation. And you can break this down into like theory or already measured values by getting the amount of energy deposited in scintillation in a ratio to Cherenkov radiation. And then this extra factor here is a correction to the amount of energy deposited by scintillation radiation. This comes from Burke's law. Essentially, without this, um, the the theory value would tell you, oh, as you get to higher and higher energies of particles, you essentially just continue to get more and more scintillation radiation. When in actuality, you reach a maximum threshold where your scintillator becomes saturated. So that's why this term is here and why it's also really important in this parameter, because without that, you get like a runoff effect. And in reality, it sort of plateaus to a certain value. But what's great about this is it's a ratio of two values that exist in your signal. So it's not very sensitive to temperature or the bias voltage of the photomultiplier, and hopefully not your sampling rate. But the weakness is, you need to get as much of that light as you possibly can. And you also need a high decay time scintillator, so that way these two peaks separate out. So this was something that was recently demonstrated by this other group in 2019, where essentially they did just that. This is, your Cherenkov peak up here. You have your scintillation peak down here. The Cherenkov is essentially happening at the speed of light in that medium. So it's instantaneous, more or less as fast as you can be, right? The scintillation, though, is much slower because it follows all those chemical decays and it trails off later on. And they were able to separate this out. And if you can separate this out, you can then use this parameter, which is what we plan on doing. So to just compare this to something that already exists that does more or less a similar thing, there are also solid-state silicon detectors. So we're using scintillators with CPMs. So this is a CPM over here. This is a solid-state like silicon detector. In particular, this is LGAD. I've worked with both of these before. They both have their own strengths and weaknesses. Like particularly if you want like really high precision, like electron measurements, these are really good. Like you can do a lot of cool things with these. But we just want something that can give us like some calorimetric particle data on high energy particles. And so in particular, we go with scintillators and CPMs because they're easy to scale to a larger area. You don't need as high a sample rate. They're pretty cheap as well. Like one of these CPMs is like $50. The scintillator is a few $100, even with all the machining and polishing as well. Okay, that's pretty accessible, which is what we're shooting for something that you could just like throw onto a space mission, right? But to go, one step further, we can kind of plot these radiation gain values versus the energy of the particle and the particle species. So again, this is more or less, we're taking those two peak values and the power of those two, and we're creating this ratio to kind of get an idea of what the shape of the pulse is. Because we have those two peaks. For certain particles, the scintillation peak will be higher than the Cherenkov peak. And for certain particles and energies, it'll be the other way around. Okay, so that changes that shape on our overall pulse. And so we're using this parameter, this radiation gain parameter, to characterize that. And we put it in decibels because otherwise it has this logarithmic scaling anyways that'll make this plot kind of abhorrent to look at. But as you can sort of hopefully see here, at high enough energies, these really separate out. And as I'll show later on with simulation values, it's actually even better than this. But so to get into the sort of nitty gritty of what is going on with this radiation gain parameter, how do we measure this? Again, we have that Cherenkov part that's coming in really fast at the beginning. Also, I'm now realizing I think my camera is flipped. So like this is my left and I'm thinking this is on the front. That might be flipped around and making this confusing. But essentially on your rising edge, you have the Cherenkov peak, then you have the scintillation peak coming on later. And so whenever you're trying to get that radiation gain parameter, your analog to digital converter reads off from your photomultiplier to get a waveform. So what that looks like is like this plot here. This is sampled on a 1 gigasample oscilloscope. And in it, I've kind of separated these out and done this all manually in Excel as my very first proof of concept is what this was. I separate out this Cherenkov peak and this scintillation peak, and I get a value of radiation gain that's 20.0 decibels. Okay, so again, that really fast part, I separate out, I get the power from that. I integrate its power in that region because this is a voltage versus time, waveform. Then I find the peak for the scintillation part, and then I integrate its power and take the ratio of those to get radiation gain. Okay. So this is it's kind of like fancy integration and ratios of integration and whatnot. But I get 20.0 from doing this decibels from doing this manually. If I just do this and I'm getting ahead of myself. This is for a cosmic ray muon. Okay, forgot to say that part. If I do this from theoretical values, like particle data group values, I get 20.1 decibels. So 20.0 looks pretty good. And even whenever I downsample this, and this is like ridiculous downsampling, to 40 megasamples per second. So like this was 1 gigasample or 1,000 megasamples. This is 40 megasamples. We still are able to, and this is now running with the algorithm as well. So this is an algorithm found that those peaks and also this valley point in between them, and calculates this just automatically. This is through a Python script, took this waveform, downsampled it, and then found these peaks and valleys and calculated this, got 20.368. So that's still pretty good. Okay. We're still pretty close to the 20.1 decibel value. So it looks promising. And, again, I can zoom in, but I already kind of zoomed in on these. But just to reiterate, the PDG value essentially is 20.1 decibels. The manual value of me doing this by hand in Excel, like a Neanderthal, was 20.0 decibels. And the Python script, even after downsampling, got 20.368 decibels. And this is also a script that I made to do this because, even though you can look up things on like Stack Overflow to do basically anything you want in Python, it's not literally anything, right? Sometimes you do have to make your own stuff. But it gets even better because at this point, I also have an ADC that's actually on the other side of my room because I've been doing a lot of this from home. I have this ADC, an FPGA board that has also gotten some events that look like the candidate events where there's this like Cherenkov peak and a scintillation peak. Although there's also a lot of noise going on here. So I need more data, essentially. But still, this looks promising. And just from putting this into Excel and doing it manually again, I got like 20 something, I don't remember, decibels, which puts it in the ballpark of a cosmic ray muon. But really, now we're going to try to like transition over to the Monte Carlo simulation of this all. This is what a simulation of a bunch of different electrons, so not cosmic ray muons, but cosmic ray electron signals look like at different energies. So more or less what's going on here is that at really low energies, you just have scintillation. Okay, because the electrons aren't over the threshold for Cherenkov radiation, right? Because Cherenkov radiation, you have to be above the speed of light in that medium. So that essentially puts a lower energy threshold. Eventually you get above that, so this peak gets larger, but the scintillation also gets larger. There's a point in here where they become very similar in size, although unlike the muon where they really get close, the electron doesn't really get that close to each other because its scintillation radiation takes off a lot faster than the muons does because it's not nearly as massive. And so eventually this scintillation peak just becomes much, much larger. But yeah, those are simulated waveforms because essentially now I'm working on this PCRD MC, so like a Monte Carlo simulation of this. So why do we want to do this? Well, particle physics, as much as we like to think it's just like nice quantum field theory and all this like cool math, it really is filled with a bunch of nasty distributions, okay? And integrals as well that don't really play nice together. And it's a lot easier to just use random numbers to go through these distributions instead of trying to find analytical solutions for everything. Okay, so that's what I've been working on. Now, previously, I used like JAM4 and Fluka for this, but I would continually run into issues where I was like, okay, what I want to do has never been done in JAM4, so I'd have to make my own JAM4 library. But then all of that gets constrained by what JAM4 allows you to do, and time again, I would run into a wall where it'd just be like, okay, well, I can't do this in JAM4 unless I make another library that can do this. So I just went, oh, okay, well, whatever. I guess I'll just invest all my time into making my own thing. And then I'll use experimental data and already existing simulations to constrain what I'm making. So that's more or less what this boils down to. I just made my own simulation instead, so I could focus on what I wanted to do in this simulation. So, the classic example of why you would use a Monte Carlo to make this more like easy to understand people who maybe aren't in experimental particle physics, you're trying to calculate something that's hard to calculate. So pi. But you wanted to do it quickly and simply. So you generate uniform random numbers in a box, and then you accept the number that are within this circle. Then the ratio in the circle versus those in the box is essentially the same as the ratio of their areas. So, pi r squared divided by r squared is pi. That's kind of what you're shooting for with this sort of thing. You use random numbers and like geometric constraints to calculate something that's difficult, like pi. So we're on a satellite. One of the things we need to do is orbit generation. So at the very beginning, I showed you these plots. These come from SpinVis, which is the European Space Agency has like this, it's like a combination of Monte Carlo and just experimental data. And it generated these plots. So these are again for our orbit and also these different particle species. I've used this as well as some other information to generate my own orbits and also generate particles based off of lat long, but I didn't put this in here because I don't want to spend forever on this orbit generation. But essentially, I'm able to generate an orbit and step it through time. And as this changes lat long values, I can change the composition of just a random event that occurs. So that's pretty cool, having a simulation that can do that, right? Because that's part of what PCRD is doing. It's flying through orbit, and what it'll see will change. So we want to know how that's going to affect our events. But I'm also working on this sky map thing. So just as a basis, I started, and this is how I came up with that sky map that I showed in the beginning. I start with these point sources. So I have the sun, which is like, even if I zoom into this, it's very difficult to see. This small trail here is how much the sun moves with respect to PCRD over a week. It's not a lot. Then I have the moon. It moves around a whole bunch over a week because it's orbiting around the Earth. And I've treated the sun as this like particle source. The moon is a particle like shield. It's blocking events from occurring. The sun is producing additional events in addition to just a uniform random in all directions, so isotropic events. And then just for curiosity's sake, I also put in the Virgo cluster and Andromeda because I was like, okay, well, what if we also had particle sources for them in addition to the sun? And then you also like scaled their distance. So as you can imagine, like the flux from these is going to be very small because they're far away. But I was curious. So this starts out with so I'm getting a little bit ahead of myself. This starts out with the bin resolution on this is the resolution of the attitude determination and control system of the CubeSat-1, which is about 0.1 degrees at 1 sigma. So these bins are pretty small. They're small enough that the sun and the moon are like, I think, a couple pixels or so. So it's not really, it's not Hubble, right? But it's still decent. But then we have to Gaussian blur this so it has the resolution of the PCRD, which is currently really bad. It's 45 degrees. So basically, it can tell you in what direction, like what hemisphere of a sphere you're in. And when you do that, it really, you get this shadow area where the moon is. You get this bright spot where the sun is. And I'm not sure if this is a faint bright spot or just a transition, but I don't think this is going to be detectable after random events are thrown in, like the isotropic events are thrown in as well. But this was where the Virgo cluster was. And, Andromeda, because it's in the same part of the sky in this simulation here as the sun, it's just completely overwhelmed. So you then generate like a week's worth of events and you see that there's this overabundance and this shadow here. But outside of that, you really can't see if there's anything going on over here or whatnot because it's just everything else is just far fainter. But this is kind of, at least I think this is interesting because what this means is that if there is indeed particle excess coming from the direction of the sun, or there's events being shadowed by the moon, we could potentially reconstruct that, okay, and get an idea of the direction of these cosmic rays and whatnot. And also, just a reminder, this is the all particle spectrum, more or less, down here. Because we can differentiate particles and their energies, we could make this mapping for, just electrons, just protons, just the absolute highest energy electrons. Maybe we just want oxygen nuclei. We can do stuff like that. Okay. So we also move on now simulating the detector. So right now we just treat the events as straight rays, and energy gets deposited along those rays. We don't have like any Coulomb scattering or anything. And then the energy deposited in the scintillators gets turned into waveforms based off of experimental values that I have. And also there's random thermal noise based off of what you set the temperature of the experiment, of the simulation to. So the amount of thermal noise will change based off of that. So if you're in a really cold part of the orbit, there'll be less thermal noise than if you're like facing the sun and you're 100 degrees centigrade. This will change. But more or less what's going on here is this is a simulated waveform. It kind of looks similar to the real ones, although this is, I think this is a 1 GeV electron from what I remember. So by that point, the Cherenkov has already gotten to like its threshold. It doesn't really get much higher, but the scintillation does continue to get higher. It still is not at threshold at 1 GeV. But the important thing then to see here is that even when you throw in the thermal noise that we would expect in space, we can still get the peak. We can still get the valley. We can still get this peak as well as this edge. and still get a really decent measure on the shape parameter and the power values for scintillation and Cherenkov radiation. And literally plotting this out, okay, for all these different particle species and energies, you can see how they sort of separate out. And I've had to do some weird scaling on some of these axes so you can see the separation between these. But stop scrolling around. These data points have error bars, okay? They're quite small, which is good. Although in some places, as you see down here, they become larger. But for the most part, they're pretty small. And so we can really differentiate these particles. You know, the electron one goes off the screen because I wanted to be able to zoom in and show how the proton, the helium, and the oxygen are all different. The oxygen one has this weird feature where because the Cherenkov turns on right here as the scintillation is going down as well, there's a sudden like peak here, but then it goes back down because the Cherenkov almost immediately reaches threshold and is then like again comparable to the scintillation or really dominated by scintillation. Um, so this is kind of an odd feature. Um, but you know, looking at the power of scintillation and Cherenkov as well, we can really see this sort of separation where these separate out into their own neighborhoods. You know, again, oxygen's doing its crazy thing here because oxygen nuclei have like what 8 protons, and this goes as the number of protons squared, but then it's also no, yeah, it just goes as the number of protons squared. So this just skyrockets because you know this is essentially um, the electron is already at its threshold. The proton's at 1 squared, 2 squared, etc. Um, but yeah, it's looking hopeful for separating these out. It's more or less what this gets at. So then to just throw this in at the end. So for right now on CubeSat-1, we're just looking to have just one PCRD and having coincidence between 2 channels of one PCRD. But in the future, we'd like to fly something more interesting in terms of physics. So, like for example, this PCRD V plus H, where we'd have nearly 4 pi instantaneous coverage because we'd have one looking horizontally and vertically, is something that I've been looking into. But also this particle optical camera where more or less you either have a CPM array or a CCD array that is coupled to a bunch of scintillators. You more or less do what you would like do with the scintillators, but across an entire array. So you can get really fine angular resolution because now you have these small pixels. This is like very similar to a lot of medical scanning technology as well. But instead of using it to image like a body, you're using it to image the sun. Because in particular, you get about 15 to 40 arc minutes, depending on how you put it together. So that's about 1 to 16 pixels for the moon or sun. So that's, you know, potentially look at the particle structure of the sun. Although again, 1 to 16 pixels is not a lot. But I also recently talked to Sasha, who I think is here, about this, about we can get better resolution at really low energies if we have something like Agile, which is silicon detectors, because they are very good at this lower energy. So having this set up where we have like PCRD V and H to just sort of tag these horizontal and vertical events, then this camera to really get a fine angular resolution, but then Agile can give us like time of flight and low energy measurements. So we can know if it came up from below as well as if it was a really low energy event. And this is really important for like those solar energetic particles as well. That right now PCRD is essentially just shielding out because we don't want to saturate the detector. But conclusion, back at the very beginning, I don't have an advisor anymore, which kind of is unfortunate. But CubeSat is pretty cool. It's launching soon. PCRD is also cool. We're going to map the sky, hopefully, and try to measure particles in a new way and do it in space. And then obviously we're simulating everything because we don't want to just randomly generate numbers, which is kind of, you can randomly generate numbers using cosmic rays, but we don't want to do that. We want to make actual measurements. The references go off the screen, and I don't think anyone cares. I want to thank Mindy as well as, my mind just went blank, Pavel and Christian. Am I forgetting anyone? I hope I'm not forgetting everyone. Basically, everyone who made the graduate colloquium possible. I'm just like suddenly my mind is in physics mode, so I can't remember like anyone's name right now. It's very frustrating. But yeah, I think this is a really great platform for allowing graduate students to talk about their research in a way that's potentially more casual than just a colloquium, like the normal colloquium. Also, Greg has really helped me with a lot of stuff recently, and I'm really appreciating of what he's done for me. So I just wanted to give him a shout out. And then also all my peers in CubeSat for putting up with me. And I didn't write this one, but I also think, Sasha, you're pretty great. And I don't know, I look forward to anything in regards to collaboration, whatnot. But yeah, that's it. Thank you. I guess this is the part where you like ask for questions, right?
Yeah. So thank you so much for giving this talk. It was really interesting. We have just a few minutes for maybe some questions if anyone has it. I will wait 10 seconds because I'm told on Zoom that is what you should do. Oh, Yoni, go for it.
This is a really great talk, Brendon, and this is something that I had heard about maybe tangentially, and I was always sort of curious on how it was actually going. You mentioned some of the requirements that NASA was looking for the Artemis missions, and part of that has been ride sharing to send small sats to orbit the moon and actually do like interesting lunar orbit science. Is this something that, if appropriately, scaled up, you could potentially send, a network of these like very, very small 3U CubeSats to the moon and like measure radiation flux there for something? And how do you expect that would like change your job?
Okay, so what you are asking is like something that I would love to do. I guess as a preliminary bit of information, Tyvek, who's the company that we're like working with, who gave us the CubeSat, they've actually put CubeSats in orbit around the moon before. So I want to say there is a possibility that that could be done in a future mission, putting a CubeSat around the moon. But especially the idea of putting up a whole bunch of CubeSats in like a giant array, that is something that I have talked about before. Like I talked about it briefly with my committee during my master's thesis. And yeah, it's a really interesting idea because the more of these you get and the larger array you can get, you can start to do really like interesting correlation measurements, particularly with like really high energy cosmic rays. You have air showers that develop. And if you have a CubeSat array that's, for example, around the moon, and a ultra high energy cosmic ray hits the lunar regolith, it'll generate a shower. And then unlike Earth, where that shower would then almost essentially be destroyed by the Earth's atmosphere because it would just absorb it, there's no significant atmosphere for the moon. So that shower then goes out into space. And if you have a CubeSat array just floating around, you can get a whole bunch of coincident events across that entire array and now say, okay, there was a high energy cosmic ray event over in this direction. And really get an idea of what is the ultra high energy cosmic ray flux through the moon or along the surface of the moon, really. But there's also, like, I've read a paper where they've looked at, like, well, what if dark matter decayed in the atmosphere and generated a particle shower or something like that? And so that's also something that you can then get a possible measure on if you have an array of CubeSats. But that's more, I mean, the dark matter measurement is more kind of out there. The ultra high energy cosmic ray particle shower is something that definitely could be done. And because there's a relatively more common occurrence of those than dark matter events, it would be feasible to do that. And at least I think it is more feasible. Yeah, it's an interesting idea. It's something that I think if we can get funding for that sort of thing, we could definitely try to do.
Great. So we might have time for one more quick question. Okay, so I don't see any hands. Again, thank you, Brendon, for taking time to do this. We appreciate you kicking off our graduate colloquium series this semester. To any graduate students who are here, if you're interested in giving one of these talks, you can email me or Christian or Pavel. We'll definitely hook you up and put you on the schedule sometime this semester. So I guess there's nothing else from me. So good evening and thanks for coming.
Thank you very much.
Bye.
Thank you, Anna.